In section 2.4, we're going to learn another shortcut for taking the derivatives of certain types of functions. In this case, it's going to be composite functions that we will deal with. There is no special sheet to go with this video, so you will need to take notes in your binder, but there is a TI Inspire file that you should have in your possession. This file is titled 2.4-notes. So what we would like to do first is just verify that the derivative of sine x is cosine x. We have seen that proof of the shortcut, but we're just going to verify it graphically, and this will give you an idea as to how the little exercise is going to be at the beginning of this video. So you want to enter your original function as f1 of x. So you'll go to page 1.1 on the calculator, and if you don't see the entry line, just hit the tab button and it should appear. So enter it as f1 of x to be sine of x. Alright. I guess, yeah, on the calculator you have to actually have parentheses around the angles, so make sure you do that. And then go ahead and hit enter. Okay, it'll show you the graph. And then hit the tab button again. And after you've tabbed, then enter f2 of x. Okay. You're going to be entering for f2, you're going to enter your guess as to what the derivative is. So we would just enter cosine of x. Alright, forgot there's parentheses around that too. Alright, and then you want to hit enter, and it will graph the cosine. Now the way we're going to check to see if cosine actually is the derivative of sine of x is hit the tab button again, and it should go straight to f3 of x, which I believe is in green on this file. Okay, and you'll see that I've already entered in a command called inderivative. Alright, and this stands for numerical derivative, and it should say inderivative of f1 of x, and then there's a comma x. Okay, that basically means we're taking the derivative of the function f1 of x with respect to x. That's why we have to have the comma x there. Alright, now I could have entered this as d dx of f1 of x. We could do that, have done that too. But I wanted to make you familiar, especially those of you who don't have CAS, wanted to make you familiar with this command right here, because instead of using algebra to actually get the derivative, which the CAS calculator can do, inderivative does it more in a numerical way, using the numbers and really using average rates of change with a really small x interval, a really small h value. So if you don't have CAS, this would be the way, or this is the way you need to deal with derivatives, is use inderiv or inderivative. Alright, so hit the enter after that and see if the green graph actually matches your, I guess it was a red graph for the derivative graph, your cosine graph. Here is what your screen should look like once you've entered those the two functions in. And we can see that the derivative graph does appear to be matching up with the cosine graph. So we're pretty confident that cosine is the derivative of sine. Now we're going to do the same little exercise, but with the function sine of 3x. Okay. Before we graph the sine of 3x on page 2.1 of the calculator, I want to just do a little review. What effect does this constant 3 have on the graph of sine x? Alright, and then of course we can check our answer. So pause and think about, maybe jot down a quick answer. Hopefully you were thinking or said something along the lines of that either it would be, I guess, a horizontal stretch, because we're multiplying the x part, so it might be a horizontal. It's not going to be a shift because we're not adding, but we're multiplying, so it's either horizontal stretch or compression. Stretch or compression. Okay, so which one is it? Well, hopefully you also remember that anytime you do something to the horizontal, to the x part and horizontally, it goes the opposite of the way you would expect it to. So it looks like we would stretch it by a factor of 3, but indeed what happens is we compress it. Okay, I'm going to mark out the stretch. It's going to be a horizontal compression, not by a factor of 3, but by its reciprocal, a factor of 1/3. Okay, and so maybe you were thinking along those lines. Yeah, let me erase that out, make it look a little better. There we go. Or perhaps you were thinking more in terms of, say, the period, since this is a periodic function. Sine of x is periodic. You might be thinking, well, that just means that the normal period of 2 pi actually gets compressed by a factor of 1/3, or it's 1/3 times 2 pi. And so you could also describe this as saying, well, the period now is 2 pi over 3. Okay? And another way, you might have even remembered the formula that the period always equals 2 pi divided by that b term, and the b term in this case is 3, so 2 pi over 3. So there are several ways to think about, anticipate what's going to happen with the graph of sine of 3x. All right, now go ahead and plug that in on page 2.1. Plug it in as f1 of x, right? f1 of x equals the sine of 3x. We can see, indeed, the effect of compressing the graph of sine of x by a factor of 1/3. The easy way to do that, I've already got the window set up to basically go from negative 2 pi to positive 2 pi. So we can see that now we're getting 3 cycles, right? 1, 2, and now 3 within the normal period of 2 pi. So that does mean we've compressed it by a factor of 3. Okay, so now it's your turn to try to make an educated guess as to what the formula for the derivative of the sine of 3x is. Okay, and once you think you know, put your guess in as f2 of x, and you can check your answer, as it says at the bottom of the page here, by turning on f3 of x, just like you did before. All right, so why don't you pause and do that, and then we'll see if you were right. Now, if you're like most students, what they usually enter in for the derivative of sine of 3x is the cosine of 3x. And there we see the graph, the red graph here. But if you turn on the green graph, which is the derivative of f1 of x, you'll see that that's not exactly what we're getting. Okay? So can you tell from the green graph here what the derivative of the sine of 3x actually is? Why don't you pause it here and make a guess, and then we'll talk about it. Okay, so hopefully you noticed that, well, a couple things. Hopefully you noticed, first of all, it is a cosine graph, right? We can see that it's peaking at the same time as the red graph, and it does appear to have the same period as the red graph, right? So that would make me think that at least the piece that you said, if you said cosine of 3x, I don't think you're far off from having the correct answer. But what we can see here is that it appears that the green graph has a higher amplitude, right? Or that it's been vertically stretched by a certain factor. Can we see what that factor is? Yeah, it looks like instead of going up to 1, it's now going up to 3. So we know that would be either a vertical stretch by a factor of 3, or you could call it the amplitude is 3. So how do we get that? Right? We just need a 3 in front. So it appears that that d dx, okay, of the sine of 3x, all right, is actually equal to 3 times the cosine of 3x, all right? So think about that, and now let's move on to the next one, see if you can get a better guess as to what the next derivative will be. The next one we're going to do, as you see, is the derivative of sine of x squared. So first thing, just let's get this entered on page 3.1 of the calculator is f1 of x, okay? And let's just look at that graph. We first want to kind of see what is going on with this graph. It appears that it still has the same amplitude. It's just going between 1 and -1. But hopefully you can see that the period appears to be getting smaller and smaller as we move, as x gets bigger, or as x gets, as negative x gets bigger. Appears like it's getting smaller. Let's see if we can make sense of what's going on there with that. I'm going to go back to my blue color here, since we're in blue. We could rewrite this formula as the sine of x times x, okay? Now, whereas before, remember we were doing the sine of 3 times x, okay? Now we're looking at the sine of x times x. Well, when it was the sine of 3x, we said the period, let's see if I have enough room here, we said the period was equal to 2 pi over 3, right? We just divided 2 pi by the number in front of the x. Well, we can kind of do the same thing here with this graph, okay? Here now, the period is not 2 pi, it's going to be 2 pi divided by x. So we can start to see why this graph is looking the way it is when we analyze it this way, right? As x gets bigger, our period continues to get smaller, okay? So at no one time, is our period constant. It is always getting just a little smaller and smaller, so the cycles keep getting tighter and tighter. And that's why the graph looks the way it does, okay? All we've done is affected the horizontal part. We have not affected the vertical part at all. If we were going to do that, we would have done something to the outside part of the function. So this is, you might want to think of this as having a dynamic period. Okay, so go ahead now and make your educated guess. Hopefully it's a little better educated after seeing what we did on page 2.1. But make an educated guess as to what you think the derivative of sine of x squared is, and then you're going to enter that, right, as f2 of x on your calculator, okay? And you can also, hit enter then to see that graph, and then go back to tab and turn on the f3 graph so you can check and see if your answer was right. Hopefully it's kind of like a fun game. So pause the video right now and do that before moving forward. All right, so now that we've got the f3 graphed, don't be too upset if you didn't get it to match. If you did get it to match, awesome job, because you're really astute at seeing what the pattern is. But if you didn't get it to match, don't feel too bad. It's a little tricky pattern. Maybe some of you got it. I'd be interested to know if you did get it on the first try when you come to class. All right, so let's see if we can make sense of this. All right, we've got our green graph here, and we can see that in this graph, just like in the last graph, remember the amplitude got bigger. Well, it definitely appears like the amplitude's getting bigger again, okay? In fact, it's getting bigger. Instead of being like a constant number like 3, it's getting bigger according to this line right here, okay? This line that's going up. Or you could say the line that's going down through the negative. You could also do that, but we'll just take a look at the line that's going up. Right? Now this line, as we see, is going right through the origin, okay? And let's see if we can kind of figure out what its slope is. All right, it's maybe a little hard here, but if I go 1 unit, let me mark 1 unit. 1's right here. How high am I going up? It looks like we're going up to 2 units here, right? Doesn't it appear that way, that we're going up 1, 2, and then to the right 1. And if we win another 1 units, we go to 2. Once again, looks like we might be going up 1 unit. Going up 2 units into the right 1. The scale is a little off. You'll have to keep in mind that the scale on the vertical is tighter than the scale on the horizontal. So we have to pay close attention to just the way the units are. All right. So it does appear that this line is the line of y equals 2x. Okay. So if you think about it, that's kind of serving like our amplitude. On the graph before, the amplitude was 3. You know, it was, I'll just, kind of sketch the line across right at 3. That was our amplitude. It was like y equals 3. So let's see if we can make some sense of this. I'm going to try to move everything up just a little bit so I have a little more space down at the bottom. All right, so I've included up here what we learned on the previous screen, that this derivative sine of 3x was 3 times the cosine of 3x. All right, and so let's just take a look, first of all, at the graph. It does appear that the blue graph, which of course has sine in it, and the green graph, which we're trying to figure out here, looks like they don't peak at the same time. Like, in fact, I'm seeing that when the blue graph hits 0, it looks like the green graph's peaking, and vice versa. So that would lead me to believe that, let's see, if we're talking about now d dx of sine of x squared, okay, that would lead me to believe that we're going to have a cosine graph, okay? It's got to be a cosine function. Now, as far as the period goes, or the the horizontal compression, it does seem like the periods are kind of compressing at the same rate. That as the blue graph is getting tighter and tighter, so is the green graph. So I'm thinking that we still want to go with maybe x squared, that is still cosine of x squared, okay? And now that we've kind of analyzed our amplitude, we're seeing that, instead of our amplitude being just a straight constant, being 3, it's actually a dynamic amplitude as well that seems to fit the line y equals 2x. So I would think that we should, instead of multiplying by 3 in front, we should just multiply by 2x in front. And perhaps that is the actual derivative of the sine of x squared. So why don't you try filling that in and see if it works for you. Well, hopefully you're getting some success here, that you're seeing a red graph that is actually conforming to the green graph like we saw on the other page. If not, something might be wrong. Maybe you're in degree mode when you should be in radians. I'm not sure, but this should work. All right, so let's move on to the next. So what is the pattern for the derivatives of these functions? And these functions that we're working with, as you can see, are actually composite functions, right? We're composing we're plugging the graph, or the function 3x, into the sine of x, and here we're plugging in the graph x squared into the sine of x. So what's the pattern? Well, hopefully you've kind of picked up on the fact that it appears that we do need to take the derivative of this outside function, right? Sine is the outside function, and every time we have taken its derivative and gotten cosine, okay? But we haven't done anything to the inside function right there. We've kind of left that inside function alone in both cases. But then we've had to multiply, outside of all that, we've had to multiply by, what is this? What's 3's relationship to 3x? And what's 2x's relationship to x squared? Yes, it is actually, this is the derivative of the inside function, okay? So that is kind of how our shortcut is being set up, all right? This is what we call the chain rule. So we are making the claim that the derivative of a composite function here, where f's the outside function and g is the inside function, is simply going to be the derivative of the outside function. So f prime of g of x, we leave the inside function alone, and then we simply multiply by the derivative of the inside function, so g prime of x. This is what we call the chain rule, and let's take a look at the next slide where we will prove this rule to be true. Please don't feel like you have to, copy all this down into your notes. If you want to use the snipping tool to get it, there is a proof of this in the book on page, I believe it's 131. I'll write that up here at the top. But they've left out a few details that I'm going to include to just make it a little clearer. Okay? All right, so let's go through this. Try not to take too much time, but we're hypothesizing that, if f of x equals g of h of x, then f prime of x is going to equal g prime of h of x times h prime of x. All right, so we're just going to start with f of x is equal to g of h of x. And you need to understand we actually have three different functions here. So let's write them out. Let's just suppose that y equals f of x, okay? And let's see, the input for h is also x. So h of x, we're going to say that equals u. And then, of course, that u is now the input for g. So g of u, we're going to say, is equal to y, okay? Because keep in mind, the output for g is the same as the output for f. So that's why we have a y here and we have a y here. Okay, so now we're just going to take the derivative of each of these three functions. So dy dx is simply equal to f prime of x. In this case, it would be du dx equals h prime of x. And we'll have to have dy du equal g prime of u. By definition, that means that dy dx over here is going to be the limit of delta y over delta x. That's just a difference quotient as the denominator goes to 0, right? That's our definition of derivative. And we do the same thing for the other two functions with their appropriate dependent and independent variables, okay? Now I'm just bringing this line right on down here, okay, recopying it, but now I'm going to multiply the delta y over delta x by delta u over delta u, right? Just a special form of 1, no problem there, okay? And then we're simply going to use the commutative property to switch what we're multiplying. So the top's going to stay the same, delta y times delta u, but the bottom we're going to switch and we have delta u times delta x, all right? And the next line, hopefully you can already guess, that's just one of our limit properties. I believe it's limit of a product, right? Limit of a product. It says we can divide, or just distribute the limit over a product. Limits are so nice that way, okay? All right, so let's go to the next page. We're just going to pick up with that line and continue on. So up top here we have the original line that we're trying to prove. This is the line that we just left off with, okay? Now, if you scroll back, you'll see we had already defined u to equal h of x. So see if this doesn't make sense. I mean, this is true just about for any function. As the delta x, as the input variable, or the change in the input variable goes to 0, it should make sense that the change in the output variable is also going to go to 0. This is true for any function. If I sketch a graph, of h of x right here, okay, u equals h of x. And we've got u on the vertical axis, and we've got x on the horizontal. All right, if we pick 2 points that are on the graph, okay, and, by making delta x go to 0, that means that these 2 points are going to come closer and closer to each other. Well, as they get closer and closer to each other, not only is the delta x going to 0, so is the delta u, or the output, the change in the output values. So this is a true statement for any function, that as delta x approaches 0, so will the change in your output values. All right, so the reason we want that is we're going to replace the delta x approaching 0 up here with delta u approaching 0. Okay, and the reason we want that is that we have delta u in the denominator of this difference quotient. So now you see we have a derivative here, and we also have a derivative over here that we always had before. So this derivative is du dx. This derivative right here is dy du. And it should make sense that dy du times du dx is going to give us dy dx. We just would cancel out the du's. Well, what is dy du? If you go back to the original, if you want to scroll back in the video, you'll see that dy du is equal to g prime of u. And you'll see that du dx was equal to h prime of x. All right? And now we're almost there. All we have to do now is replace u with h of x. Okay, remember u is equal to h of x. So we do indeed have that our derivative of our composite function f ends up being g prime of h of x times h prime of x. And there we go. That's proof. QED. Let's write it. QED, which was to be demonstrated. Now, it's very important that you get this stuff in your notes, okay? This is on page 131. It is called the chain rule. And this is just kind of the setup here, that if we have y equal to f of u, and I don't agree with their choice of letters here, but that's what they're using. If that's a differentiable function of u, and u equal to g of x is a differentiable function of x, then y equal to f of g of x will also be a differentiable function of x, all right? Such that, and then here's the real part, right? You need to put a star by this. This is the part to remember, that the derivative of that composite function will be f prime of g of x times g prime of x. If you want to think of it, in terms of the Leibniz notation, you can. It does make sense, in terms of multiplying here, that dy dx would equal dy du times du dx. It's not usually how I remember it, okay? Now, another good way to also think about this, okay, I've rewritten that top line right here, but now you can also think of it as that the derivative of a composite function with respect to x, or your input variable, is the derivative of the outside function, okay, with respect to the inside function. So you take the derivative of the outside function, leave the inside function alone, okay, you still have that g of x in there, and then you simply multiply, or so times the derivative of the inside function with respect to x. That is the chain rule in words, and it's not a bad way to remember it either. Page 130 of your textbook has a kind of a neat example demonstrating the chain rule here. What we have are three axles, okay? The axles, of course, are the long stems here, okay? And you can think of axle 1 as being like, here, I'll use red here. Think of that as being y. Think of axle 2 as being u, and think of axle 3 as being x, okay? And you can see they've actually given us the radii of each of these axles, or at least of the gears. So, gear 1 is a radius of 1, and gear 2 is a radius of 3, and gear 3 also has a radius of 1, while gear 4 has a radius of 2, okay? And so that can tell us something about how many times you'd have to turn axle 1 to get the gear 2 to go around once, or to get axle 2 to go around once, all right? Now, also keep in mind that circumference, of course, is 2 pi r, so the circumference of gear 1 would just be 2 pi, the circumference of gear 2 is 6 pi, right? And then 3 is 2 pi also, and gear 4 would be 4 pi. So we can use these to kind of figure out what the rates would be, all right? If we want to look at axle 1 and axle 2, it should make sense that we would have to actually turn axle 1 3 times to get axle 2 to go around once, because the circumference of gear 2 is 3 times bigger than the circumference of gear 1, okay? So we could write that by saying that dy du is equal to 3 over 1, okay? 3 would have to go around, axle 1 would go around 3 times to make axle 2 go around once. So the rate is 3 to 1 that we're spinning axle 1, all right? And now we can kind of do the same analysis between axle 2 and axle 3. It looks like axle 2 is going to have to go around twice to get axle 3 to go around once, right? So comparing their circumferences, we're comparing the circumference of 2 pi to 4 pi. So we could write that by saying that du dx is equal to 2 over 1, okay? Du is spinning, or axle 2 is spinning twice to make axle 3 spin once, okay? So of course the question is, what is the relationship between axle 1 and axle 3? How many times would axle 1 have to spin to get axle 3 to go around once? And you're right, it's going to be 6 times, right? We could certainly say that dy dx is going to equal 6 to 1. And of course, how do we get that from the other two rates? We would just multiply them. So this is showing once again here that dy dx, okay, is indeed equal to dy du, okay, times du dx. And that is the chain rule, actually. This is the derivative of the outside function with respect to the inside function being u, okay? And then we multiply that by the derivative of the inside function with respect to x, all right? And if we do that, we get the derivative of the composite function, dy dx. So let's go ahead and get into some practice problems like what you'll see on the homework, okay? Let's do this first one together. So we have, g of x is equal to the square root of 3x plus 2. Well, the first thing we might want to do, like we've done with power functions, is to rewrite that square root, okay? Let's write it using an exponent. So it's 3x plus 2 to the 1/2 power, okay? And hopefully you're already seeing that we have a composite function, right? We have an inside function is 3x plus 2, and our outside function is the 1/2 power, okay? So how do we get g prime? Well, we're just going to take the derivative of the outside function, okay? So that's the 1/2 power, and just leave the inside function alone. So we know that with the power rule, we need to bring that 1/2 down, right, and multiply. We're going to leave that inside function in there, and then we just have to take the exponent down by 1. So 1/2 minus 1 would give us negative 1/2. Okay, and we're going to leave that 3x plus 2 inside there and don't do a thing to it. All right, but now we need to multiply by the derivative d dx. Let's see, d dx right here of 3x plus 2. And of course, that's not a hard derivative to get. So we'll just end up with g prime of x equal to, 1/2. And of course, the derivative of 3x plus 2 is just 3, so let's bring that out to the front here. So it's 1/2 times 3 times 3x plus 2 to the negative 1/2. Okay? So now all we have to do is just to rewrite it. We don't want to leave negative exponent in our answer. Okay? So since we have a negative there, we know we're going to end up with a fraction. And let's see, I believe the 2 in the 1/2 is going to be in the bottom. The 3 is going to stay up top. And then the 3x plus 2 needs to come to the bottom. So it would be 3x plus 2 all to the 1/2 power. Or if you'd rather rewrite it as 3 over 2 root 3x plus 2, that's fine. Okay? But that's our derivative for g. Just as a quick variation on the last problem, what if it had been g of x equals 1 over the square root of 3x plus 2? Could we do that using the chain rule? You might think we probably need to use the quotient rule here, okay? But if you rewrite it in an effective way, you'll see that you don't really have to use the quotient rule here. We could rewrite g of x, okay, as simply 3x plus 2 in parentheses all raised to the negative 1/2 power, right? And now that means g prime of x, right, is going to be what? Negative 1/2 times 3x plus 2, don't do anything to that function, all raised to the negative 3/2 power. And then we simply need to multiply by 3. So that would give us, what, a negative 3 on top and the 2 on the bottom, and then we would just have 3x plus 2 all raised to the 3/2 power on the bottom. So very quickly, you can avoid using the quotient rule sometimes pretty easily. Another little variation would be, what if you had something like this, 3x plus 2 squared, okay? We could use the chain rule on this, but of course another way to approach this problem would just be to go ahead and distribute it out. Just make sure you're thinking this is 3x plus 2 times 3x plus 2, and of course that would give us what, 9x squared plus, I think we'll have plus 12x, right, plus 4. So you could do it out that way and then just get g prime by doing the derivative of each piece. So that would just be very quickly what, 18x plus 12. So You don't always have to use the chain rule if this exponent is small enough, okay? But keep in mind, what if instead of being a square, what if that had been, 3x plus 2 to the 6th power, all right? If that was the case, then we really would want to use the chain rule. Let's just take a quick look at that on the next slide. All right, so if it's 3x plus 2 to the 6th power, I don't want to expand that out and then use my power rule. It certainly would be much easier just to use the chain rule, right? We would just say it's 6 times 3x plus 2, and then that would be to the 5th power, and then all we'd have to do is multiply by 3. So very quickly we would get a nice short answer to what the derivative of this function is, whereas if we expanded it, it would take forever to do that. I want to let you do this next one on your own, but I do want to remind you that the notation we have for raising a trig function to an exponent is a little misleading. Okay, we need to remember that sine squared of x is really the sine of x, right? The sine of your angle x squared. Okay, so it might be a little easier to write it with parentheses like this before you get started. Okay, so why don't you pause it right now, and then you can check your answer. I'm going to go ahead and tell you what the answer is. Did you get f prime of x to equal the sine of 2x? I'm going to be actually impressed if some of you said yes to this, and I'll tell you why in just a minute. But my guess is you probably didn't get this, okay? And you're wondering, how can this be the right answer? All right, well, let's take a look. I bet you did this. Hopefully you saw, okay, the outside function is the square function, so f prime of x is going to equal, let's see, we need to bring the 2 down, and we're going to leave that sine of x alone, and of course 2 minus 1 gives us 1, so we have 2 times the sine of x, all to the 1st power, and then you needed to multiply by the derivative of the inside function, which is the derivative of sine of x, so that would just be times cosine x. So I'm thinking you probably got 2 sine x times cosine x. Okay, well, guess what? That means you got my answer also. Okay, because remember, 2 sine x cosine x, that's the double angle identity for the sine. All right, good job. One last example here before we look at a couple of textbook problems. If you want to try this one on your own, I think that'd be great. You just pause it right here. Otherwise, we'll take a look. It's got a little twist to it. Okay, so in taking this derivative, we can definitely see a composite function. Let's rewrite it so that it's tangent of 2x, and then all of that to the 3rd power, right? So certainly the cube is our outside function, tangent 2x is our inside function, okay? So let's just go ahead and deal with it that way. Let's see, I'll write d dx right here. So that would mean we need 3 to come down, and then everything else is staying in there, and it'll be to the 2nd power, so we've got the tangent of 2x, all right? And now we need to multiply by the derivative, right, d dx, of the tangent 2x. But hopefully you've kind of noticed, that function, that inside function, is also a composite function. So that means we need to use the chain rule on it, okay? So let's see, I'll conserve a little space. So I've got 3 times the tangent squared of 2x, right? And now we need to do the chain rule on tangent of 2x. So what's our outside function here? Yeah, it's the tangent, right? Tangent's our outside function. So what is its derivative? If you need to go back and look it up, it's a good idea to do that. I'll provide the answer this time, but tangent's derivative is secant squared, right? So it would be secant squared of whatever's inside there. We're not going to do anything to the inside function, so we'll just leave that 2x alone. And now we need to multiply by the derivative of the inside function, so times d dx of 2x, okay? And so we end up with 3 times the tangent squared of 2x, all right, times secant squared of 2x, and then times 2, okay? So you can start to see maybe with this example why they call this the chain rule. We're just linking up the chains of outside functions. You know, first we did the cubic, the outside function cubic. We got 3 times the tangent squared of 2x. Then we took care of the next outside function, which was tangent, and its derivative was secant squared. And now we're going to take care of the last function and multiply by its derivative. So we keep multiplying by the next layer's derivative down, right? The next layer down doing its derivative. All right, so let's just gather up some things. So we got a 3 and a 2 that are multiplying, so we'll end up with 6 times the tangent squared of 2x times the secant squared of 2x. And that is our derivative. You might try to think if anything's going to cancel, you know, if you change the sine and cosine. I don't think anything will, because remember, tangent is sine over cosine, so we'd have sine squared over cosine squared, and here we'd have 1 over cosine squared, so nothing's going to really cancel, so we might as well just leave the answer this way. I just want to point out a few of the problems that you're doing on this assignment that are actually very similar to each other. And one reason I point these out is you see a lot of this on the AP test, and many times students will freak out when they don't actually have a formula to work with, okay? So let's take a quick look at number 97, part B. I think you have parts A and D in this problem. If we were doing part B, we want to find, we're trying to figure out what f prime of 5 is, okay, for each of the following, if it's possible to. So in B, we know that f of x equals g of h of x, okay, so what we first need, of course, is f prime of x, if we're going to get f prime of 5. So let's just use our function notation. We know that f prime of x is going to be g prime of h of x, g prime of h of x, and then we have to multiply by h prime of x. So that would mean that f prime of 5 is going to be g prime of h of 5, okay, times h prime of 5. Let's see if they gave us enough information to get this, okay? So we'll have g prime, what's h of 5? They're just going to come out and tell us that h of 5 is 3. So we have g prime of 3 times h prime of 5. They told us h prime of 5 is negative 2. Okay? Now, did they tell us what g prime of 3 is? Let's see. No, they did not. They didn't tell us what g prime of 3 is. So because of that, we don't have enough information. We'll just say not enough info. Otherwise, we're very close to getting that answer. Okay? All right. So you'll do the same kind of thing when you're working with, say, in letter A. Of course, you're not going to use a chain rule because you don't have a composite function, but you do have a product, right? And so you should know that you would use the product rule in that. So just write it out just like I wrote this out, and then try to fill in the numbers that you can, okay? Of course, you're just going to replace the x with 5 in the problem. You have a very similar type of exercise in number 98. I think you have letters B and C to do in 98, okay? With letter C, it looks to me like you're going to need a chain rule in there, but not with letter B. You just have a 2 times the f of x, so you know how to treat that, okay? Now if we were doing, say, letter D, just real quick, we would have s of x is equal to f of x plus 2, and we need to figure out what the derivative values are for s. So we would need to figure out, okay, so s prime of x is equal to, now we have a composite function here, so I need the derivative of the outside function. So the outside function is f, so I'm going to go f prime, leave the inside function alone, x plus 2, and I'm going to multiply by the derivative of the inside function. So I'm going to multiply by derivative of x plus 2. Well, that would just be 1, okay? So if I wanted to know what, say, s prime of negative 2 is, all right, I think that'll work, negative 2, then I would need f prime of negative 2 plus 2 times 1. Well, that would mean I need f prime of 0 times 1. So it looks like s prime of negative 2 would equal, let's see, f prime of 0 is negative 1/3, so it would be negative 1/3 times 1, or negative 1/3. Okay, and we'd fill that in. So that's kind of how you do this. Very similar to the other problem. You also have number 99 on this assignment, and very similar to the two problems we were just looking at before. You don't have a formula, but you do have the function notation. So get your derivative for h prime first, okay, using that function notation, and then you're going to get your information like what's g prime of 1 or f prime of 1. You're going to get all that off the graph, okay. For instance, just to kind of help here, what would f of 1 be, right? Well, f of 1, of course, just read that off the graph, is equal to 6. But what is f prime of 1, all right? F prime of 1, well, we need what's the derivative, or what's the slope of the graph at 1. And we can see that looks to be about 1. Looks like it's a slope 1, so f prime of 1 would be 1. Okay, so you'll put that information together to help you figure out what h prime of 1 is. Okay, and of course you can do the same thing with g. All right, so this does it for the chain rule video. Hopefully this helps you get going on the homework, and I hope the video is not too long, but I can definitely tell it's not the shortest video.